So let's now look at how to compute the convolution, and first we're going to look at the algebraic approach. And the algebraic approach just means that we're going to do the integral using calculus. However, in order to get some intuition, we're going to actually kind of sneakily put in some of the graphical approach there so that we understand what these integrals mean. And we'll see in doing so that drawing a picture is, of course, always a big help when solving a problem. So the learning objectives for this section are to manually compute a CT convolution in the time domain and to simplify calculations using LTI properties and sort of standard formulas. And by that I mean like making a template formula and applying the template and using LTI system properties. So we saw that quite a bit in the discrete case. Okay, so what's the basic idea? If for a particular x and h, I know the output signal y, so I know that here's y of t when I convolve this x of t and this h of t, then you can easily calculate just from this, you can calculate if I delay by tau, the input signal I get a delay by tau in the output signal. And if I multiply by a gain alpha, I get a multiplication by a gain alpha in the output signal. So once you've computed a template y of t, you can use these properties to compute convolutions, which are essentially delayed and gains applied to the known template that you've already calculated. You can just apply those operations to the output signal. So we can often calculate convolutions just using calculus. So let's look at an example. Here there's my x of t, and here's my h of t. And I'm going to show you, so we want to show this system is an integrator. And we'll see what that means in a second, but basically we want to show that if the impulse response is the unit step function, then this system essentially acts like an integrator. Okay, so we just plug things into the formula. We have e to the minus alpha tau now, u of tau, and then the u of t over there becomes a u of t minus tau, because we have h of t minus tau. And then now we apply the step functions. And we apply the step functions by saying, okay, u of tau means that the signal as a function of tau has to start at, it can only start at 0. This integral can only start at 0 because u of tau kills everything for tau less than 0. Similarly, u of t minus tau, what does u of t minus tau look like? This thing looks like this, and here's t. So this is u of t minus tau. And remember, this is the tau axis. So this thing kills everything that is above t. So the integral can only go up to t. So this is an integral from 0 to t. The output so this is our y of t. Our output at time t is the integral from 0 up to time t of the input signal x of t. So we can do this integral. This integral is pretty straightforward. You've known it from calculus. And then we should make sure we multiply by this u of t to indicate that the signal starts at t equals 0. Right? So that's what this u of t does. It clips the signal. So now that we have this, we can, of course, calculate other convolutions using properties of LTI systems. We can do this delay by 3 on the output, and a gain by 3 in the input. And so what you get is the same output that we had up here, but now with this gain of 3 and this delay of 3 applied here. And so this is just the output. So remember, we can apply any sorts of gains and delays to the input or the impulse response, and we'll just see those reflected in the output signal. So that's why I talk about using it as a template. So here's a slightly more complicated example. Here we have x of t is e to the minus at u of t. So we again have our decaying exponential. So this is x of t. Always draw a picture. And then what is the other signal? The other signal is u of t. So it starts out at 0. And then it drops off at you get a minus u of t minus tau, 0. So at tau 0, it drops off, right, to 0. So we just have a box. So this is just a box. So the question is, what happens when we take this decaying exponential and convolve it with a box. That's really graphically what's going on, and we can write it out algebraically. We again have e to the minus a tau, u of tau, and then we take this whole thing and we flip it, essentially, and think of t as the delay. So we get u of t minus tau minus u of t minus tau minus t0, and so this is because we're plugging in, again, t minus tau in for t. Okay, so just sort of get a sense of this. This is a box that goes from, if this is the tau axis, this is a box that goes from t minus t0 to t. Okay, so what happens in this integral? Well, if t is less than 0, then there's really nothing in this integral. And that's because this function h of t minus tau is not overlapping with x of t. So we get 0 over here. So hopefully that's clear, and then that it translates over here into the final answer. Now, when t is bigger than 0, but not quite as far as t0, then we're going to get some sort of partial overlap. So we're going to see that we have some sort of partial overlap here with this x of t. And then we're just going to get the integral from 0 to t, because we're going to get this, again, we're going to get this limiting of the integral and the u of t. So u of t is going to clip off everything from this box except for the part that goes from 0 onwards. So that's going to be tau equals 0 to t, e to the minus a tau d tau, and that's going to hold until t equals t0. Then finally, when t is greater than t0, we're going to get essentially just the integral from t minus t0 to t, that's the width of the box, times e to the minus a tau d tau, right? And we get this. So just doing these integrals, we get these two other cases. And as you can see, I just sort of did this graphically, so let's actually see what it looks like graphically. So I got this from the DSP first at Georgia Tech. This is this CT convolution demo, and we'll talk about this more in the next video. But here we can see, here's our box. Here I'm just doing it for 0 to 2, so tau 0 equals 2. And we can see at time t equals -1, the flipped version of h of t doesn't overlap at all with the decaying exponential in blue. So the output is equal to 0. So now we're going to slide this box forward. So we can see at time 0, the box and the decaying exponential just start to overlap, so the integral is still going to be 0. So what happens next? What happens next is the box starts crossing over the decaying exponential. So we get y of t is 1 over a, 1 minus e to the minus at, and that's going to hold from 0 up to t0. When t0 happens, the full box will be in covering up the, will be overlapping the exponential. So that looks something like this, right? And at this point, now the box is going to slide forward, and it's going to not be covering the first part of the decaying exponential, but just a chunk of length t0. So proceeding forward, you can see now we're only integrating this area here and trying to find its area, and then so when you multiply the two signals, you can see you're just getting this this slice of a decaying exponential, and these slices are getting smaller and smaller as you increase t. So you can get this, you see you're going to get this decaying behavior in the output signal. And you can see as we go along, you get this decaying behavior. Okay, let's look at another example which we can do just plain old algebraically. So we have two decaying exponentials for x and h, e to the minus at u of t and e to the minus bt u of t, and we'll assume that the magnitude of a is smaller than the magnitude of b. So again, we can plug into the convolution directly. Just plugging it in, we get e to the minus a tau u of tau, and then we get, this remember is h of t minus tau, just plugging in this formula here. Okay, well, looking at this e to the minus bt you can factor out because it doesn't depend on tau at all. So we factor out this e to the minus bt, and then u of t clips the integral starts the integral at 0, and u of t minus tau stops it at the integral going farther than t. And we have e to the minus b minus a tau d tau. Of course, we know how to integrate an exponential. So we get 1 minus b over a, e to the minus b minus a t minus 1 u of t. And so we can multiply this minus b of t, and we'll get e to the minus at. We get this, just doing a little bit of algebra, e to the minus at minus e to the minus bt over b minus a u of t. So you can compare this to the discrete time version we did with decaying exponentials and see how the formulas are similar or different. So let's do a little example. What's the output of an LTI system with impulse response 3 e to the minus 2t u of t to an input 2 times e to the minus 3t minus 3 u of t minus 3? Okay, so we write out the convolution. We write out, so we have the total delay. So the total delay is coming from just this u of t minus 3 e to the minus t minus 3. There's no delay in the h of t. And there's a total gain of 2 times 3 of 6, so this is the total gain. And then the b minus a term is going to be 1. So we can just plug it in to our formula. So here we're plugging in to the template that we just calculated on the previous slide, and we get this answer here. So it takes a couple of times to just sort of practice this. And so what I think would be a good idea to do is, of course, to try these yourself. So why don't you try calculating the system h of t with input x of t for these different combinations. And if you want some more practice, you can make up different x of t and h of t and use the same argument of convolving them with total gain and total delay, and use those as more examples. And if you want to try this whole process of designing a template, try to pick two signals maybe that we haven't considered here as an x of t and h of t, try to convolve those, and then realize that you can apply the delays and gain property to calculate the outputs for manipulated versions of those signals.